We want to know the volume in milliliters of acetic acid, and this is 0.2 molar acetic acid HC2H3O2. It's mixed with 13.2 milliliters of 0.2 sodium acetate. And it gives a buffer. You should have already known that it's a buffer because I have an acid in its conjugate of 4.2, I think. I said yeah. So in order to solve this, I'm going to use the Anderson-Hasselbalch. pH is equal to pKa. I'm going to find out on the back of the exam. So I look on the back, it's 4.74 for acetic acid, plus the log of the base over the acid. Okay. Now the pH I know, it's right here. And what I recommend to do first is solve for B over A. Okay, so solve for B over A. Okay, because here's the problem. If I read the question again, these two, let me circle them in green. This right there, and then this one right here are mixed. What problem is that going to cause, anybody, in my calculation? What will change when I mix those two? The molarities, the concentrations will change. So I can't put those numbers in B over A. Because they're going to change once I add more. They'll become more dilute. I need that final volume. So really, solve for B over A is what I'd recommend doing first, just to get a little bit of the mess out of the way. And then, A, here's the acid. It's, well, I need another page. Okay, the acid, I'll just call A. You would get it like this, when you say M1V1 equals M2V2. The initial molarity is 0.2. The initial volume is V. And then the final molarity, we don't know. And the final volume is 13.2 plus V. So see, this is the problem. We don't know this final molarity of the A. Okay? And then the same is true with the base. We're not going to know its final molarity. So one way to get around that is that you know the moles of each. Well, you know the moles of the base. And once you know the moles of the base, you can find the moles of the acid. Because in B over A, you don't have to just put molarity, you can put the moles. So B and A can be moles or molarity, and the moles won't change as you pour things together, only the molarity. You're still going to have the same amount or same moles in there. So you're going to be stuck in a lot of different ways that you go here, unless you just go for the moles. So I think the easiest way to do this is find the moles of the acid and the moles of the base. So the moles of the base is going to be the easiest. It's just 13.2 milliliters times 0.2 molar, and this will be so many millimoles. So this will be B. If I zoom out a little bit more, this will be B, right here, this B, or this B. So that'll allow you to find A. And then the moles of the acid is going to be the unknown volume times 0.2 molar, and this will equal A. So you're going to use this answer, you're going to put it in B, and then you're going to solve for A, and then you're going to solve for volume. Did that kind of make sense, or is that too much crazy?
Can you do the last part one more time?
Okay. You're okay with B over A? You can find that number?
Yeah.
Okay. Then you're going to find the moles of the base. It's these two numbers multiplied.
Okay.
You get that?
Yeah.
Put that in B and solve for A.
Oh.
And then you'll know A.
And then you can find the volume.
Got it?
Yeah.
Cool. Okay, next. Yes? Why does it end up being the same? Because the final volume will be the same when you put them together. So it's moles over the final volume divided by moles over the final volume. Those will cancel out. Yes? Page 48. Okay, hold on. What number? Question 1. Okay, let me just show you this one. Oh, whoa, okay. This one right here. Okay, how do you find this? If you're given a pH, it's actually easier than you would think. Usually all of those A through E are buffer pairs. Okay? And so they would all potentially work, but you want the buffer pair that will buffer something at 2.1. So a buffer will work best when its pK matches the pH. So all you're going to do is take the negative log of all 5 of those, and the one closest to 2.1 will be the best one. And that's it. Cool. Yes? Okay. Look for this one here. Number 16. Is it this one right here? I wouldn't ask you something this difficult on this exam. Yeah, so you can see something more like this on the final. Number 16, right there. It's page 62. Okay. Yeah, I saw your hand next, actually. Yeah. 52. Number 3, you said? Okay. This one also, it'll be easiest if I just show this one. This is page 52, number 3. Where does Kp equals Kc? Kp equals Kc times RT delta N. It's a formula for it. And so, when the only times that Kp equals Kc if delta N is equal to 0. So what you're looking for is where do the moles of gas of reactants equal the moles of gas of products. So take a look, for example, in case A. In the reactants, there's 4 moles of water. In the products, there's 4 moles of H2. Is that okay? That's a good possibility. In in part B, there's 1 mole of water, but 2 moles of both the gases in the product. So in that case, they're not equal. So only A is equal so far. In case C, there's 2 moles of the SO2 plus 1 more of the O2. That's a total of 3. And then on the right-hand side, there's 2. So 3 and 2 are not equal for C. For D, there's 1 mole of H2 on the left and 2 moles of HI on the right. So only case where the products equal reactants is case A. Is that all right? Okay, cool. Who's next? Yes?
When you do an ice table, when do you know, like, assume that x goes to 0?
Okay. I'm going to turn to the reader. The question was, how do you know when x is equal to 0 in an ice table? And assuming that this question existed, I told you at the end of chapter 15. It's a good question because it happens a lot. You need to know when to do it. So I just wanted to summarize all the scenarios where it would happen. This is page 80. Page 80 in the reader. What K values would cause x to be small? Ka for weak acid, Kb for weak acid, Ka1 for weak acid, or Ka2 and Ka3. So basically, anytime you have a weak something, you can make that assumption. Or Ka2 and Ka3, but that probably won't come up in any of your math. So if you want to just really boil it down, it's when you have a weak acid or base. That's going to happen. Yes?
So earlier when we were going over the strong, dilute strong acid,
yeah.
we were able to know that the pH would be between 6.8 and 7.
Okay, when I was doing the dilute strong acid, how did I know that the pH is going to be around 6.8 to 7?
Yeah.
Because, so a strong acid normally expect the pH to be about 0 to 1 or to be below 0 even. The more and more dilute it gets, the weaker the acid strength is because it has less protons to donate. And so when it gets so dilute that it's near the pH of water, I know that the pH of water is 7. So a very, very dilute acid is just going to bump it a little bit on the acid side. So that's why it's really, really close to 7. And that's going to happen anytime you have a dilute. Okay. Yes? Yes. Unless you want to pass.
No.
Okay.
11 on page 8.
Page 58. Oh, wait. Wrong book. Okay. 58. Alright. We were looking at this one right here. Okay. I have to write this one out. This one's too crazy. Okay, this is a type of question though. You'll see this occasionally on exams. We have NH3 plus F minus plus H3O plus goes to HF plus NH4 plus OH minus. I want you to recognize this reaction. Okay. What you might probably don't, because it's not a normal reaction. But what you could recognize is that, hey, I see these two are similar, and I see that these two are similar. Okay? Let me write those out. So the NH3, okay, I think somebody knows how to do it now. I know the general reaction for a base is this, for NH3, involving it and its conjugate. Is that okay? All right. And for HF and F minus, if I write it backwards because the HF is on this side, the general reaction for an acid, I'm just going to write it backwards, okay? Okay? Whoa. There we go. Goes to H3O plus F minus. Is that all right? Okay. Oh, cool. Add these up. And you're going to get this reaction. You see how they're added up? Yeah, so then this becomes a kind of our Hess law type problem. I need the KB for this, which is in the back of the exam. And I need, what is this? Not Ka, but, not Ka for HF, but to the minus 1 because I flipped it. So then K total, when I add it up, is, what do I need to do to both of these when I add? I multiply Kb times Ka to the minus 1. Okay? Cool. Yes? This is a typical type of question. You'll see it every once in a while on exams. Yes? Spring 11. Okay, this one here is probably easier to show you so I don't have to write it all out. Okay, number 4. I want the one with the lowest pKa. Does that mean the Ka is large or small? Anyone? Yeah, if the pKa is low, just like the pH, then the Ka is high. Okay, if the Ka is high, is it strong or weak?
Strong.
Relatively strong. Okay, does that make sense? Okay, so I'm looking for a relatively strong acid right now. All right, this is just the acid doing its thing here. Okay, here what happened? The acid actually lost that hydrogen. Here, in the first case, it lost the hydrogen on the oxygen, here on the nitrogen. In this case, it lost it on the carbon. Okay, so we're losing it from the oxygen, and then the nitrogen, and then the carbon here. Okay, what happened here? Something crazy happened, and it lost it on the carbon and the oxygen. That's just ridiculousness. Okay, this lost it on high nitrogen, carbon, and oxygen. Okay, so each time you lose a proton, you know it gets harder and harder. So D and E are the most ridiculousness possible. Okay. So really A, B, and C, losing each one hydrogen, are the ones we're focusing on. Okay, so look at your periodic table. Carbon, nitrogen, and oxygen. Of those three elements, which one are the most acidic of those three? Oxygen, because it's more electronegative. So you're going to pick the one, the strongest acid is the one that's losing it from the oxygen, which is case A. Do you need to look at what the distance is from the central atom? No, that won't matter in this scenario. That could matter later in organic chemistry if you have a pretty big molecule. But this is just, a linear 3 in a row, so it won't matter. Okay, yes, way back there.
Page 53, number 12.
Okay. All right, number 12. Are you talking about this one right here, the sulfur?
Yeah.
Okay, I need to write that one out then. Okay, we've got this is number 12, page 53, spring 13, 3.24 grams of sulfur in 40 grams of benzene. Boils 0.81 degrees C above the boiling point. So what variable is this one? This is just straight up delta T, because it's that much above the boiling point. Okay, determine the number of sulfur atoms. So this is Sx. We don't know what X is. Kind of like 2A, the empirical formula stuff. We don't know how many sulfurs are in it. Could be 1, 50, 8, 4, whatever. Okay, in one molecule of dissolved sulfur, Kb of benzene, Kb, the constant, is 2.53 degrees C per molal. All right, so in this case, this is the second type. There's two types, the plug and chug and then the more. In this kind of example, you're going to solve for molality and then do a unit conversion to what we want. Okay, let's try that. So, delta T equals I, K, M. Okay, delta T is right there. What's I? Anybody? Just 1, because these are all molecular compounds. There's no ionic compound here. So sodium chloride would be an example of ionic, where there's a metal. K is given. It's right there. And then so we're going to solve for M. Okay, so you solve that on your calculator. It's just plug and chug. And then molality, remember that's moles per kilogram. Now we need to, second step is unit convert to get to what we want. Well, in this example, to get to what we want, I really will want, because whenever they ask me for a formula, I really want to find the molar mass. Now the nice thing about this one, they gave me the grams. It's 3.24 grams of sulfur. But I need the moles. If I had the moles, I'd find the molar mass, and then you'll see how I solve the problem. So I'm going to find moles. Okay, at 1 gram per mole, they give me mass, I need moles. Okay, so to find moles, all I need to do is get rid of these kilograms here, and I know there's 40 grams of benzene. Remember, kilograms is of benzene or the solvent, and kilograms per 100 or 1,000 grams. So this will give me moles, which will go right there. Now what I'm going to do, look at your periodic table. See, sulfur is 32 grams per mole. So my answer better be a multiple of 32. If my answer is 32, there's 1 sulfur. If it's 64, there's 2 sulfurs, etc. Is that okay?
Yeah.
Okay, cool. Okay, who's next? Just want to make sure somebody knew. I think you haven't asked a question yet, have you? You did. Did you ask? You did too. Oh, you did. Okay, yes, you're on. Okay. Okay. Let me flip over there. Going over to 2010. Oh, this is an indicator. Somebody asked me about indicators earlier. Okay, question 6. Let me see if I need to write this. Let me write something down here for this one. This is a fairly typical indicator question.
What page?
Page 66, number 6, spring 10. Phenol red is an indicator that is yellow below pH less than or equal to 6, and it's red at a pH greater than or equal to 8. So there's a color change that happens between 6 and 8 for this phenol red indicator. I want to estimate the pKa of phenol red. So let me show you the answers. The pKa is just where it's changing its color. Okay? So that's where the acid is changing color. So in our example here, it's changing color between 6 and 8. So what number is between 6 and 8? Looks like 7. So I take that one. I forgot who that's now. Oh, Wilbur. Is that cool? Okay, yeah, that's it. Okay, way back there. Yes?
On the same page.
Same page. Oh, perfect. You two are synchronized.
13.
13. Okay, this is a similar sort of question to a little bit earlier. So this is a great counter example of the ammonia HF example we did a little earlier. Let me write out this reaction. NaOH plus HCl goes to NaCl plus H2O. Okay, I'm going to get a different color pen now. Okay, identify all the spectator ions for me. What's the first one? Okay, cross that out. Cl. Okay, anything else? I think we're good. So let me rewrite this now, okay? Oh, what reaction is this? It's almost Kw, but not exactly. It's flipped. You see that? It's inverted. So whatever Kw is inverted, or 1 over 10 to the minus 14, which is probably 10 to the plus 14, is going to be your answer. Is that okay? And wherever the heck that went. I'm sure you can find it now. It looks like it's B. Okay, let's see, have you asked a question yet? You did? Anybody new? Okay, yes, I just want to, we'll repeat, yes. 80, number 16. This one right here? Okay. This is kind of the Hess's law type problem, but with K. So what you want to do is say, how can I get to the overall reaction from these? You'll see that the intermediates, or whatever, don't appear in the overall, and that would just be, let's see, H2. Well, somebody's moving crazy over there. H2. So it looks like H2 is intermediate. I really need the bottom reaction flipped. Is that okay? So I'm going to flip the bottom reaction, a negative, and to match it with the H right there, what do I need to multiply it by? A negative 2. That means I'm going to take this and square, negative square, negative 2 squared, whatever that is. Raise it to the minus 2 power. And then, for the top one, here, if I want this to match, if I want HO to match or O2 to match, what do I need to multiply by? Also by 2. So this will be squared. And then, when I add the reactions, what will I do to the K, anybody? I'm multiplying them. Is that alright? Okay, now I think we can repeat. Okay, no, did you have a question already? You haven't. Okay, we have another new person, yes. 54. Okay, hold up. Yes, this one. Which one? So there's a couple things I want to think about before I go on. One is, I just want to double check that it's not in this. Okay, you should double check that, but I don't think it's in here. And so it's not something I'm just going to read off. Okay? All right. Now, second thing, notice that what's different? Well, this molecule has a hydrogen on the oxygen. Okay? But notice this molecule does not have a hydrogen on the oxygen. You see that? Only on the carbon. Now look at the periodic table and compare oxygen and carbon. Which one's more acidic? Oxygen. So the one that has the hydrogen on the oxygen should be more acidic. Is that cool? There we go. Okay. Yes?
What about the second row?
Second one. And the third one. Okay. You all are funny. Okay, for the second one, what's the difference, anybody?
There's more O's.
More O's, so we're thinking resonance. We're not comparing element to element. We're thinking resonance now. And so the one on the right has more resonance, so it'll be a stronger acid. Third one, what's the difference here? Yeah, on the left there's two hydrogens, and on the right there is just one. So what is this thing we're looking at here? It's from a polyprotic. They're actually a conjugate pair. So I'd pick the one that's the acid, aka the one with more hydrogens on it. It's the one on the left. That's it. Okay, now we're starting to repeat, I think. Yes. Spring 11, number 80. Yeah, bad news for you, there's no 80. 18. Oh, success. Similar problem then? The second one. Okay. Oh, that's that one. What did I tell you to do first? Yeah, it's in the table. One of these has, you look up both KAs and pick the bigger number. No. Is there a way to do it without the table? No. Not in our class. Yes?
Okay, number 6 on page 53.
53. This one. Okay. Which is most likely true in this scenario? Okay, let's just think in general. For this scenario, is K large or small? Anybody? Well, let's see. Is equilibrium, where is it? It's on the right or the left-hand side? At the right. Wherever it's stabilized or where the line gets flat, that's the equilibrium side. So the right-hand side is equilibrium. Okay, is K large or small again? Large, because there's more products than reactants in equilibrium. So K is large, so it's either A or B. Okay, this graph describes reaction which the choice is most likely true. Initially, so what's true initially for Q? Is Q large or small? And I'm talking about when time equals 0. Yeah, products are 0, reactants are a number above 0. So that means Q is 0, so Q better be smaller than K. Is that right? And K is large? Okay. Yes?
Same page number 7.
7. HCl reacts with strontium hydroxide in aqueous solution. Okay, in the first case, there's 0.5 moles of HCl. In the second case, there's 1 times 0.25, but there's 2 hydroxides, so there's 0.5 moles of that. So there's equal moles of acid and base, right? So it looks like 7. Neutral. No?
SR going to dissociate completely.
Yeah, it's going to dissociate completely because it's a strong. It's a strong, and the SR is an, what's it called? Spectator ion, or conjugate.